All right, good afternoon. Here we are again for part 2 of our discussion on the kinematics and kinetics of, and dynamics of three-dimensional rigid bodies. So next, I wish to look at energy considerations for these bodies. We'll just look at energy considerations. In particular, kinetic energy. So kinetic energy as well is going to be a bit complicated, or be a bit more involved. So if I look at the kinetic energy of particles forming a rigid body, so kinetic energy. Forming a rigid body. Well, the overall kinetic energy is going to be T is equal to, well, first let me label this here. Well, something like this. Well, I guess I can just go like this. T is going to be equal to 1/2 mv squared. Mv squared, that is the mv bar squared, that is the velocity of the center of mass, plus, so this is the kinetic energy of the whole thing in relation to the center of mass, is translational kinetic energy, plus 1/2 times the summation of I equals 1 to n of delta mi, so the summation of the individual kinetic energy with respect to the center of mass. Vi bar prime squared. Or we could also say this is equal to 1/2 mv bar squared plus 1/2 times the summation. I could change this to a omega cross Ri if I wished. Summation I equals 1 to n of omega crossed into Ri, quantity squared times delta mi, or equal to, if I wanted to break this into pieces, looking at each along their the different axes, 1/2 mv bar squared plus 1/2 times ix bar omega x squared plus iy, or I bar y, times omega y squared omega y squared, oh, there's no bar in there, sorry about that, omega y squared plus iz, I bar z, omega z squared, and then we have to get into the interaction terms, omega z squared minus 2 ixy, ixy, omega x omega y, omega x omega y, so this is basically interactions here, minus 2i yz, 2 times omega z, omega y omega z, omega y omega z, minus 2 I zx, 2i zx times omega z omega x, omega z omega x. Then I could also say, if at some instant the axes correspond to the principal axis, then we could say that then the kinetic energy would collapse to T equals 1/2 mv bar squared plus 1/2 times x, and so now we're dealing with the rotational kinetic energy here, so that we'll have translational and rotational. Ix bar omega x prime squared plus iy prime bar, or I bar y prime times omega y bar, omega y bar prime squared, and this is about the center of mass, times I z prime bar times omega z bar prime squared. This is a nightmare, in case you can't tell. And all of this is equal to the overall kinetic energy. And so, with these, if you're so motivated, with these results, the principles of work and energy work and energy and conservation of momentum, or conservation of energy, work, energy, and conservation of energy of energy may be applied to a 3D body. In short, if you have a system that is just moving in 3 dimensions freely, if it's completely unrestrained in terms of rotation and translation, yes, you can apply energy. Yes, as you can see, there are energy equations that you can use. There are momentum equations that you can use. But the short of it is, it gets very complicated very quickly. I hope you like doing matrices. So if I then look at the kinetic energy, I could also look at the kinetic energy of a rigid body rotating about a fixed point, or with a fixed point. So if there's one point that is fixed, well, this would be a slightly different equation. And here, the total energy, total kinetic energy, T, would be equal to 1/2 times, here we have some more fun, Ix, omega x squared plus Iy, omega y squared, plus Iz, omega z squared, and now here comes the fun part, minus 2Ixy, so we're going to see some parallels to what we saw previously for momentum, Ixy, omega x, omega y, minus 2I yz, omega x, omega z. So the interaction terms, minus 2 Izx times omega z, omega x, omega z, omega x. And if we're dealing with that fixed point O, if the axes O, x, y, z correspond instantaneously fit that on the page, instantaneously, with the principal axes, O, x prime, y prime, z prime, then T is just going to be equal to 1/2 times Ix prime, omega x squared plus Iy prime, omega y prime squared, omega y prime squared, plus Iz prime, omega z prime squared here. And we could look at that as well. Okay. So let's think about that. Okay. Now, let's see, what is the essence of this that I really want to get at here? Let me show you an example of what a 3D problem would look like. Okay, so say I had something like this. Consider a rectangular plate of mass m is suspended by 2 wires. It's suspended by 2 wires. And we have plates, we have points here A, B, C, D, A, B, C, D, C and D, and the center of mass G here. Center of mass G here. And let's say this has dimensions lowercase a and lowercase b. Width A and height B. Width A and height B. And height B. Then, and this thing is hanging from 2 cords, hanging from the ceiling by 2 cords, whose length won't really matter. Okay. Then a certain impulse is applied to this. It's struck by an impulse perpendicular to the plate. So there is going to be a impulse, F delta T, applied to this plate. And it's hit in a direction perpendicular to the plate. So, again, this has mass m, and we want to find immediately after impact find A, the velocity of its mass center G, of mass center G, and B, the angular velocity of the plate. So what makes this so difficult is that this is obviously a 3-dimensional problem. We are, if the force was in line with the plate, this would be a lot easier. It would be a 2-dimensional problem. It would be a planar problem. But this is obviously a 3-dimension. So it's just to make things even more difficult, it's not striking at the center of gravity. It's striking off center. So that is going to make things a great deal more complicated. Okay? So I do want to work through one example of this if I can. And first what I'm going to do is I'm going to draw out the same kind of diagram that we've done many times before. So let's see. Now, the initial momentum is 0. So I'm going to do I'm going to apply my same kind of same initial momentum plus impulse equals final momentum method. However, what is the initial momentum? It's just a plate hanging from the ceiling. The initial momentum is 0. So Since initial momentum is 0, then we can simply say that the impulse is equal to the final momentum, or at least defined as final immediately after the collision. So if I draw this out here, I want to draw this plate, and I'm going to show all these forces on the plate and the appropriate delta t's and dimensions, etc., etc. So I'm going to have center of mass here, center of mass here, and center of mass here, and so this will be W delta T, and then I have my force being applied here, F delta T. Again, this is going to be along the axis and perpendicular to the plate. So I guess the negative Z axis. So F delta T. And then I also need to consider the forces. And if this was simply at rest, we could assume the tensions were the same, but because they're not, they need not be the case. Well, because it's a off-center impact, that need might be the case. So this would be TA, the tension at point A, times delta T, TA delta T, and TB delta T. And then we actually label a coordinate system. I think I'm going to make things a little bit simpler and define the x-axis and the y-axis as going right through the center, the mass center. Let me fix that. So this is going to be my x-axis and the negative x-axis. The y-axis, so this would be going through the center of the plate, basically, even through the middle of its depth, although the depth isn't going to be important here. Y, and then I would have Z coming out of the page. So positive Z is going to be coming out of the page here. So F delta T is actually, I misspoke earlier, it's not going to be directed along the Z axis, but it will be directed in the negative Z direction. And then I can say that this thing is going to have a few things. Let's see here. Let's say this. Now, how do I want to describe this? Let's think about this. Okay, so let's look next at what kind of momentum this thing will have. And this is where it gets a little tricky, because sometimes it won't have a momentum in every direction. Well, let's consider this. Let's say here, just a moment. V2 and Vx, yes, Vxi and Vxk, yes, that makes sense. Okay, so let's look at what kind of momentum it will have immediately after the impact. And I don't know why my plate got bigger, it just seemed to for some reason.
The illusions the air gives us.
Yeah, it's just those optical illusions in the air. Yeah, that's it. It's not my poor drawing skills. It couldn't be that.
Definitely not.
Definitely not. Because everyone knows that before you get hired as an engineering instructor, they make you pass a rigorous drawing exam. You know, you have to, huh?
Yes, you wasted.
Yeah, I aced it. It was a solid 3 days and 3 nights of drawing. No rest, just days and days of drawing in front of the best masters in the field. It was so rigorous. It was amazing.
Your graphing skills are actually pretty good, like
Oh.
in the paper.
Oh, really?
Like all the diagrams.
Oh, okay, thank you. Well,
Fantastic one.
not on this though. Yeah, I can actually do pretty decently with actual pen and paper hand drawings, but I can actually create some decent little sketches in Paint. But anyway, that's more useful than you know, because especially in many office environments, it's like you're sitting there and you're like, wait, the only tool I have to draw on this computer, and I can't install additional software because the computer's locked down. All I have is Paint. I only have Paint. So you get better with Paint. But anyway, I can create a basic engineering sketch in Paint.
A box.
No, with dimension lines and everything. I can do all that in Paint. Okay, so let's look at what kind of momentum we're going to have. Well, in the final momentum, I'm going to say that I'm going to have momentum in both the x, in terms of translation, I'm going to have momentum in both the x and the z direction. X and z direction. So I might have, first I would have Vx, Vx like this. Let's say like this, Vx times Vx times I, the unit vector I, and then I would also have a momentum in the z, linear momentum in the z, so some Vz, z bar here, or sorry, not Vz bar times k. And why not j? Any idea? Why not j?
It's supported by two different.
Because it's supported by two different ropes, yes. These are going to absorb that force, most likely. And the reason we can get something in the x is because we're going to get some amount of translation. We're going to get some amount of rotation, I should say, and that will come with it some amount of translation in the x direction. Then, in terms of rotation, I will have something about the x-axis, which would be hxi. And then I wouldn't have any rotation about the z-axis because this is pointing in the same direction. I can't create rotation about the z-axis with a z-force, but I can definitely about the y. So we get hyj. Hyj. So then I can say that v is equal to vxi, vxi plus vzk. Vzk. And omega is equal to omega xi, plus omega yj. Omega yj. Okay, then I can say that we can, because these are principal axes, we can reduce these down. Since here, since the x, y, and z axis are principal axes of inertia, well, then hg, every time I say hg, I just want to add wells to it, but anyway, hg, thank you for telling me that, Wacom, I did not need to know that. Hg is equal to ix bar times omega x times the unit vector I plus iy times omega y j hat in the j direction. Then what I want to do next is apply the formula for moment of inertia of a rectangular plate. And so I would do this as 1/2 or 1/12 mb squared, mb squared. That is the formula for, this is the moment of inertia of a rectangle, mb squared omega x times I bar, ri hat, or unit vector I, plus 1/12 a squared times omega y j. Omega y j. All right, so I now have an expression for the angular momentum here. So that's working out. And I can then apply equilibrium, applying the principle of impulse momentum. So the principle of impulse momentum and momentum. So actually that's going to be one of my final terms that angular momentum will be useful. Principle of impulse and momentum yields two equations. Yields two equations for linear momentum and two for angular. So basically every degree of freedom is going to give us an equation. Every degree of freedom or every axis where something is present gives us an equation. For linear momentum, and two for angular momentum. And two for angular momentum. All right. And if so I want to solve these then. So I'm going to solve for these equations. So solve the horizontal components for the horizontal components. Components of linear and angular momentum. Of linear and angular momentum. Okay, and so, well, first I could say, well, looking in the x direction, I know that this has to be equal to this. These have to be equal to each other. And looking at this, that if I said, if I looked for a force in the x direction, let's do that. Well, 0 equals mvx. Oh, and vx then is just going to be equal to 0. We have no impulse in the x direction, so even though I hinted earlier that we might actually get some x motion from that rotation, it turns out that we don't. So that does hold true. Then if I look here, negative f delta t, so now looking at the z-axis, is equal to m vz, so v bar z is equal to negative f delta t over m. So this is v bar then, well, is equal to vx, let me just call that vz. V bar is equal to vx plus vy plus vz. Actually, I should probably just have a bar in each of these. Bar, bar, bar. Bar none, or bar all. However, since this is equal to 0 and this is equal to 0, v bar is just equal to negative f delta t over m. And I believe that was one of the original quantities we wanted, wasn't it? Let me double check that. Let's see. Yes, the velocity of the mass center. That's one of the things we originally wanted. Oh, and this is going to be in the k direction, so in the z direction. So we already have one of our quantities. Next, I want to look at I want to find the omega. So I'm going to look at both the hx. I can say hx is equal to 1/2 BF delta T, just setting things equal to each other, and HY is equal to negative 1/2 A F delta T, just considering the directions. And then this is equal to, if I replace this here, I can say this is equal to 1/12 MB squared omega x, and this is equal to 1/12 M A squared omega y. Or omega x is going to be equal to 6 F delta T divided by MB, or omega y. So basically we have two different expressions that hx is equal to, and one from our equation, one from our diagram, and one from our previous equations for the principal axes systems. And omega y, and so we set them equal to each other and solve for omega. We can get that omega, this is omega x to be clear, not omega times x, it's omega sub x. And so here omega x and here omega y will be negative 6 F delta T divided by MA. And so then finally the overall omega would be equal to 6 F delta, that's a 6 on a G, 6 times F delta T divided by MAB times AI plus BJ. AI plus BJ. And that is the final answer there. So we have our V and we have our omega, and that's what we looked at. So again, we set up a diagram, we worked through the process, we balanced our momentums, we worked through the equations, and that is the general idea. So that is the basic idea of working through energy and momentum, or at least for energy, of three-dimensional systems. And we can look at more complex problems if we wished. But what I really wanted to do today was get you some brief exposure to handling three-dimensional problems. I could go on, but again, on here, I'm not as concerned as I could be about three-dimensional motion. I really just want to get you some exposure to the material, so I think I'm going to let you go a little early. All right, that'll do it for today, and thank you.